So here, rather than having them linearly arranged, I've now got them at right angles to each other. And you can clearly see that they're not in equilibrium. The ring is being firmly held in place by the pin. And if I were to remove this, you can see it would start to move. Now you might be able to estimate exactly where the ring was going, but we can work this out precisely. And we can do this in two ways, the mathematical way or by drawing a scale diagram. Today we're going to look at how to draw a scale diagram. When drawing a scale diagram, we're trying to model the system that we've got here on paper. We need to be accurate and precise and as clear as possible. Let's think about how we might represent this. So at the moment we've got two forces that are at right angles to each other, and the forces are represented by these masses, both of which are 5. So let's go over to the paper and draw that situation. Using my squared paper and my ruler, I'm going to line it up. Now I know that that first force line was 5, so to represent that I'm going to use 5 squares, 1, 2, 3, 4, 5, to show the first force. Now the second force was at exactly 90 degrees, so I don't need to use my protractor for the moment. Again, I'm just going to use the squared paper. So 90 degrees and 5, 1, 2, 3, 4, 5. So this is a representation of what we're looking at in our diagram. If I take that diagram and put it on top here, I can show you how. There we can see the two lines at 90 degrees representing the force. The lines are of equal length because the forces on each side are the same. So how do we work out where the resultant force is? This is where we need to draw something called a parallelogram of forces. The resultant force will always be the diagonal of your parallelogram. So what do we know about a parallelogram? Well, the key thing about a parallelogram is that both the sides are parallel. So therefore, the side that's opposite here will be parallel to this line. So the way to draw this is to move your ruler parallel and slide it up and along. Now we know that it's going to stop here, but we can continue those lines on, as it might help later on with trickier examples. We also know that the side opposite to this line will be parallel to this. So we line it up parallel and we slide it across to where it meets the end of this arrow, and again we join it up. This diagonal point here is the end of the resolving force. We then draw the diagonal of our parallelogram. That red line is our resolving force. We can now work out the size. Because it's a scale diagram, everything is in proportion. So we know that this line here, which represented 5 squares and is 5 centimetres, represented 5 newtons. So 5 centimetres equals 5 newtons. We therefore know that 1 centimetre equals 1 newton. This is a nice, simple conversion, because to go from 5 to 1, we divide by 5, and we need to do the same to this side. We can therefore use that measurement to work out the size of our resolving force. If we measure the size of this line, and this is where you need to be precise, we can see that this line here is approximately 7.2 centimetres. So using our scale from earlier, we know that to go from 1 to 7.2, we need to multiply by 7.2. We need to do the same to this side. So we know that this force will be a force of 7.2 newtons. We can check whether this seems sensible by putting our diagram back onto our real life version. Here you can see our estimate that we believe that the ring will move in this direction. And again, if we take this ring off, so it's not suspended, you can see that that's where it will freely start to move. Let's have a go at another example. Here I've moved the angles slightly, but I've kept the masses the same. At this point we've got 5 newtons at 0 and 5 newtons at 140 degrees. See if you can draw a scale diagram and predict the size of that resolving force. And I'll go along and show you how to do it as well. So we'll start off by drawing our representation. So our first force, again, was 5 newtons. So we're going to draw a line that is 5 squares long. 1, 2, 3, 4, 5. But in this example, our angle is 140 degrees away. So for that, we're going to need to use our protractor. To do this, you want to place your protractor with the origin square on the line. You then want to make sure that it follows along. Now our line was at 140 degrees. So we're going to go following around using the inner side till we get to here, 140. And we're going to make a small mark. We therefore know that the force is acting along this line here. However, we need to think about how long that line needs to be. Because we're using equal forces of 5 newtons, the line is still going to be 5 centimetres. So line your ruler up and then measure along 5 centimetres. This represents the force diagram that's shown. And again, I'll show you very quickly what it looks like. So here's our diagram, and again it represents the forces that we've just drawn. To find the resolving force, we need to complete our parallelogram. So we know that the side that's opposite to this side will be parallel. So again, we make our line parallel, we move it up and across, and we draw our line. And again, it's better to draw a line further than you need, like so. We also know that the opposite side here is going to be parallel to this side. So again, we get this line parallel, and we're going to be sliding it along until it joins this point here, like so. And again, we're going to draw our parallel line. And we end up with our parallelogram, as shown. The diagonal from the original point, so from the point here to the point here, will be the size of our resolving force. So again, we can join our line up, remembering our arrow to show the direction of our force, and there we have our resolving force. Just like previously, we also need to find the size. So in this example, we knew that 5 newtons equaled 5 centimetres. And so again, 1 centimetre equals 1 newton. We then need to find the size of our line. So we're going to measure it carefully with our ruler. And we're going to find out that this equals 3.9 centimetres. And again, using our example, we know that it will represent 3.9 newtons. Let's go from 1 to 3.9, we multiply it by 3.9, and we want to do the same to each side. You can also see how important it is that we choose a simple conversion. It's made my answer very easy to convert between my ratio and my actual answers, because I've chosen a nice simple ratio to use. Again, we can check to see whether this looks right. If we line our example up, we can see where the ring is trying to go. And if we put this in the middle, we can predict that the ring is going to want to move over to this point, somewhere around about here. If I lift this up and try and leave it freely, you can see that's the point where it's going to start to want to move towards. So now you've had some practice at how to draw our resolving diagrams. So I'm going to upload a sheet of questions that I want you to have a go at, and you'll also find them in the link below. Have a go at those questions and then come back to check your answers. As always, happy sciencing.